Hey, what's the matter? Chemistry. It's our continuing study of matter and its changes. Here we'll talk about electron configuration and continue on with that. Importance of valence electrons, formation of ions, ionic and covalent bonding as we go forward. This is Unit 2, concluding material in Unit 2. It's Chapter 5 in our textbook. Here we talk about electron configuration. This is a representation of the arrangement of electrons in the space around the nucleus. Periodic table reveals the patterns in how these electrons that each of the atoms of our elements are arranged. This arrangement informs us and improves our understanding of the elements' behaviors. And we'll be looking at the periodic table very often and seeing these new kind of designations of what we call blocks on the periodic table. Here is the S block. Here is the P block. And here is the D block. And here is the F block. Now we know that the numbers here going across in rows, these are called periods, and there are 7 periods going up and down, sometimes called columns, but these are groups, also known as families, and there are 18 of them, but we have 8 main groups, and they are 1, 2, jump across here, 3, 4, 5, 6, 7, 8. These are the main group, also known as representative groups. We can predict and can talk about the elements in these main groups with much more confidence and predictive power than the other groups, the transition metals in the middle, and yeah, those metals less predictable than the main groups. So let's jump right in and pick 2 elements, argon and potassium. Potassium is K on our periodic table, argon AR. Locate them on the periodic table, you'll see argon. Argon is in group 8A, all the way to the right in the group of noble gases, and potassium all the way to the left, group 1A, part of our alkali metals. And you'll see how many electrons they have. And that also corresponds to the neutral atom, and it's also the number of protons present, and it's their atomic number. 18 electrons. If we were to designate where those electrons are, we'd use this filling order diagram here, and we would go ahead and place those electrons into their energy levels. The first energy level has 2 electrons. We show them like this, 1, 2, and we go to the second energy level. Second energy level has the S and the P sublevels, could contain up to 8 electrons. Well, for argon, we would do the same. We would fill these. That's 4, and 5, 6, 7, 8, 9, 10, and the third energy level, 11, 12, 13, 14, 15, 16, 17, and 18. Those are the 18 electrons for argon. And if we were to write the electron configuration, that would be, we'd write that out, 1s2, 2s2, 2p6, 3s2, 3p6. Okay, these exponents, as we've learned, are the electrons, and we've placed them into how we can organize them and understand them in their respective energy levels. We see that argon has 3 energy levels, and if we looked at the periodic table, we would see that corresponds to the period that argon is in, the third period. And we can also see, we'll talk about valence electrons. Valence electrons are these electrons in the highest energy level. Those are the valence electrons. And we see that there's 8 of them. 8 valence electrons. 8 valence electrons, that's a special number. That is the number of valence electrons that all elements want to achieve to become a stable atom. Stable atom with filled s and p orbitals. So argon is, in its neutral state, a stable atom, meaning it's not reactive. And it is content, it won't bond, it won't lose, it won't gain electrons. It's content as it is. The noble gases, all noble gases are stable. They all have complete valence shell electrons, complete s and p electrons. Now, let's take potassium. Potassium has all these electrons plus one more. One more. It is in the fourth period. It's in the 4th energy level. Just one valence electron. One valence electron. So it has a lot to do to get to this stable 8 electrons. So what potassium does, it's a metal. All metals, what they do to achieve their octet is they lose electrons. They lose electrons. And so in the case of potassium, it loses this one electron. It gives it away. In fact, it gives it away to a non-metal. Non-metal such as chlorine or bromine or even oxygen or sulfur. I mean, non-metal that welcomes receiving electrons, and that's what they do. They gain electrons to achieve their octet. But metals always lose electrons, and in losing electrons, they become an ion. Right? So it loses this electron, and now it falls back to the 3rd energy level, and it does have a full octet. It has the octet similar to argon. Okay. And in losing that one electron, of course, we know that now it has one less electron than protons, and it becomes an ion. Becomes an ion. In fact, it becomes a cation. Cation. When we're an ion and we're positive, we're a cation. If we're negative, like chlorine would be, they would become chloride, and it becomes what's called an anion. It's a -1 ion, known as an anion. Noble gases, all located at the far right column of the periodic table, have completely filled valence level electrons. Helium has the 2 electrons in its first energy level. First energy level only can contain up to two electrons. Other noble gases, including neon, argon, krypton, all have 8 valence electrons, which completely fill the s&p orbitals. These elements are stable, unreactive. They generally do not combine to form atoms with other compounds. We describe their stability using what I mentioned there, the octet rule, and which states an atom is stabilized by having its highest occupied valence energy level filled. And if we wrote out the electron configurations for sodium, phosphorus, and chlorine, and in blue, we see the valence electrons, these valence shell electrons. See, sodium has 1 valence electron, phosphorus has 5, and chlorine has 7. We call the inner electrons, also called core electrons. Notice that each of these configurations contain first 2 levels, sometimes called the inner. If we add electrons, the change only affects the valence level. Since the inner electrons do not change, we often could simplify the way we write out electron configurations. And we use the noble gas notation shown there. In addition to convenience, there's another advantage using the noble gas configuration. The noble gas configuration allows us to focus on the outer electrons, the valence level electrons. The formation of chemical bonds involves changes in the outer electrons. The inner electrons do not get involved with bonding. Let's look at another example and write the electron configuration for selenium using noble gas shorthand. Identify the inner electrons and the outer electrons, the valence electrons. And from the periodic table, we see selenium has 34 electrons. So let's begin with writing the full electron configuration shown there. The first 18 correspond to argon. We can therefore rewrite using the noble gas shorthand as shown below. The electrons within argon configuration are the inner electrons. The remaining 4s, 3d, and 4p levels are the outer electrons. The valence electrons are only those in the highest energy level, however. And in this case, the energy level its highest is the energy level 4. And selenium has 4 valence electrons in, I'm sorry, 6 valence electrons in the 4th energy level. Therefore, there's 6 valence electrons for selenium. So, to complete its octet, selenium must bond in a way to acquire or to share in a way to get 2 more electrons. Finally, let's look at the electron configuration for ions. Recall that ions are particles with an overall positive or negative charge. Ions are a vital part of chemistry, and so it's important to understand their electron configurations. Let's begin with an example. What is the electron configuration for sodium atom? What is the electron configuration for sodium ion when it has a +1 charge? Let's construct a table, have that here, to show both the electron configuration and the noble gas shorthand for both species. We begin with the sodium atom. Its atomic number is 11, so that the neutral atom, the electron, shows its 11 electrons. Now, we see that in its highest energy level, there's 1 electron. It has 1 valence electron. And what happens, it is a metal, it loses that electron. And after it does that, now it has 8 in its new outer valence shell. And in doing that, it now is a cation and a new electron configuration shown here. And that's also the electron configuration of the noble gas neon. Here's a second example. What's the electron configuration of oxide ion, which is oxygen ion with a charge of -2. As before, let's begin with the neutral atom. Oxygen atomic number is 8, so that the neutral atom has electron configuration shown here in blue, or a noble gas shorthand shown to the right. Oxide ion has a 2- charge, so we have 2 more electrons than the neutral oxygen. Its new electron configuration is shown there, 1s2, 2s2, 2p6, the electrons that are gained by the atom, now an ion. Now we have an octet in the valence shell. And with the noble gas shorthand, it also has an electron configuration similar to neon, or the same as neon. So it has gained 2 electrons, and that's the reason why it is a 2- anion. Notice the similarities between these two examples. The oxygen atom gained 2 electrons to give the electron configuration 1s2, 2s2, 2p6. This configuration filled the valence shell and is very stable. The sodium atom lost an electron to give it the same valence shell configuration, also very stable, both having the electron configuration of neon, the noble gas. The loss and gain and sharing of electrons is central to understanding chemistry. The idea that atoms will gain or lose electrons and either fill or empty their highest occupied electron energy levels is central theme. And you'll see that the study of the patterns of bonding, and you'll see this in the study as we go further with the patterns of bonding and reactivity in future chapters. Incidentally, we call these isoelectronic, having the same electron configuration. These two ions have the same electron configuration. They are isoelectronic. Electron configuration is an integral part of our understanding of the periodic table. In the late 1800s, Dmitry Mendeleev organized the periodic table based on chemical and physical properties of the elements. Many of these properties depend on the element's electron configuration. Here, we'll explore the relationship between electron configuration and the periodic table. Let's begin with these three elements. We have lithium, sodium, and potassium. All of these react violently with water. They all form a +2 charged ion. So let's write the electron configuration for these three. And there's their number of electrons. Now, you'll remember the number of electrons is, as a neutral atom, is the same as the atomic number, which is the number of protons. Notice that these all have a S1 configuration, S1 in its electron configuration. They have similar behaviors because of this electron configuration. On the periodic table, these are located in 1A, in group 1A. Now the one corresponds to 1 valence electron. Let's look at another example. Fluorine, chlorine, and bromine all form a charged ion, a -1 anion. Let's look at their electron configuration. They're shown there. And they are in the same group. They are in 7A. 7A, check your periodic table. And having atomic numbers and protons and electrons of the neutral atom shown there, 9, 17, 35. If you look at their electron configuration, we could see in their valence level, they have 7 valence electrons, corresponding, of course, to the group they're in, 7A. Very close to filling their octet. And they do that very efficiently. Having almost filled octet, they have a very strong ability to acquire, to gain one electron, or to share it if it's interacting with another nonmetal. But with the metal, it very efficiently acquires one electron to complete that valence shell. Periodic table is organized based on elements' masses and properties, but it's also organized based on its electronic structure. For example, in the first period, or row, we have electrons only in energy level 1. The elements in period 2, going from lithium to helium, have electrons in energy level 2, and so forth. For any atom, we can determine its highest occupied energy level from the row or period that it is in the periodic table. The columns or groups running vertically on the periodic table correspond to the outermost or sublevel electronic configuration. Every atom in the first column, the first group, have one valence electron, have an S1 in its electron configuration. The second column, or the second group, all have an S2 as its outer energy level. Once we understand the periodic table, it's very straightforward to determine the electron configuration that occupies the highest energy level. Now let's look at the major groups. On the right-hand side of the periodic table, this group contains elements with highest energy level in the P sublevel, having P1, P2, P3, P4, P5, P6 electron configurations. The transition metals in the middle of the periodic table have outer electron configurations consisting of D1 through D10. The inner transition metals, very large atoms, have outer electron configurations corresponding to F1 through F14. Because of what we just discussed, the 4 blocks in the periodic table are sometimes called the S block, the P block, the D block, and the F block, based on the highest energy sublevel that the elements in these blocks, electrons, occupy. Understanding the organization of the periodic table also makes it unnecessary to memorize the filling sequence of the sublevels. With a glance at the periodic table, you should be able to tell the sequence in the sublevels as they fill. As you become more comfortable with the organization of the periodic table, sulfur in period 3, this means its highest energy electrons are in level 3. It's located in the p block and at p4. Therefore, its electron configuration is, its last in its electron configuration is p4. So look at a couple more examples and write the configuration of the highest energy level occupied at the sublevel for potassium and iron and phosphorus. For potassium, it lies in row or period 4, and it's in the S1 group. And therefore we have 4S1. That's its highest energy level, which it has 1 electron there. That's its valence electron. For phosphorus, lying in period 3 and group that has the configuration of P3 for its P3P3, and for iron. Iron is in the D block, and it is in period 4. But this is 3D, so it is 3D6. Iron is slightly different because the D block falls after the S block of the higher level. So the D block in period 4 actually corresponds to the energy level 3. Let's do one last example, write the electron configuration for aluminum. Aluminum, this is 3A, group 3A. So that will immediately tell us what? It tells us there's 3 valence electrons. And it is a metal. And it's in period 3. To write the full configuration, we would start out with the noble gas that is in the immediate period before, which is neon. And for neon, we'd have 3s2. Then we'd move to 3p, and that completes the electron configuration for aluminum. Jumping ahead a little bit, if we were to write what's called the Lewis dot structure for aluminum, you would write the aluminum symbol and then draw its valence electrons around it. That's called the Lewis dot diagram. Now, to become stable, this is its neutral. Aluminum, being a metal, it will lose these electrons. It'll lose the valence electrons and become an ion. What kind of ion? It would be a cation. It will be 3+. Recall that we can identify main group elements using the numbering system 1A through 8A. These numbers give us a quick reference to identify the number of valence electrons in these main group elements. For example, carbon, silicon, germanium. They are group 4A. Each of them have 4 valence electrons. In summary, the periodic table is organized not only by mass and properties of these elements, but also electron structure. The highest energy level of the element is indicated by the period or the row. The columns indicate the number of outermost electrons and whatever the indicating rather in the electron configuration, what is that outer electron shell. Chemical bonding involves changes in the atom's outer, aka valence electrons. Recall that the valence electrons are the electrons in the highest occupied energy level of the atom. Because of each sublevel sequence filling, the valence electrons involves only S and P sublevels. Since 2 electrons can fit in each suborbital, in the sublevel, and there's 6 so there's in the S sublevel there's 2 electrons, in the P there are 6, and that's where we have the octet rule. S and P sublevels needing to be filled for an atom to be stable. Often that results in atoms becoming ions. For the main group, we can quickly determine the number of valence electrons, as we've said, by the group number in the main of the main groups. It's also the number, the valence number. For example, nitrogen is in group 5A, so it has 5 valence electrons. Neon in group 8A has 8 valence electrons. In order to visualize chemical bonding, it's often helpful to draw what I mentioned earlier, these Lewis dot diagrams, or also called symbols. In these diagrams, Lewis dot diagrams, they represent the number of valence electrons. We could quickly draw the Lewis dot diagram for representative elements in each of our groups, as shown here: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. The octet rule. Again, an atom is stabilized by having its valence energy level filled. Noble gases already have that filled, as represented here for neon. However, other atoms can fulfill the octet rule by gaining or losing electrons to form ions. Or we'll also see they can do this by sharing electrons, and that is reserved for nonmetals. Many chemical compounds are composed of ions. Recall that ions are atoms or groups of atoms that have an overall charge. And now we'll look at different types of ions and learn how to name each of these. Again, here's a way to predict the ions that will, what charge they will have. Group 1 will lose 1 valence electron to form a +1. For example, these ions. Group 2 lose 2 electrons. Group 3, also 13, but this is 3A, will lose 3 electrons. Group 14 or 4A does not lose electrons, but they don't gain them really, but they'll start sharing electrons. Group 15, however, or 5A, can gain 3 electrons, satisfy their octet, and become a -3 anion, as shown here. And notice the names here: nitride, phosphide, arsenide. 16 or 6A, they have 6 valence electrons, will gain 2 and become 2- ions, like oxide, sulfide, seleniide. And group 7A or 17, they gain 1 electron, become 1- fluoride, we call these fluoride, chloride, bromide, and iodide. And group 18, noble gases don't become ions, they are already stable. Transition metals in the middle, well, they can have more than one charge, they can have more than one configuration. For example, iron could be iron 2+, it could lose 2, or it could be 3+. The transition metals could have more than one, what we call possible oxidation states. There are some that only have one oxidation state, for instance, zinc and silver, but they're less predictable. So let's begin looking a little further at charged ions. We said the main group and groups could form cations or anions. You could see examples here. And the purpose of forming ions, we said, is to fill that octet. Neon already filled. Sodium needs to lose an electron to fill its octet. See that happen here. Sodium with its electron configuration of 3s1 at its highest energy level, but it will lose this valence electron and become neon, losing an electron that could be gained by another atom to fulfill its octet. Magnesium will lose 2, become magnesium 2+, cation. Transition metals also tend to lose electrons and form positively charged ions. However, transition metals do not follow the simple pattern that we see with the main group elements. Transition metals typically form ions charged between 1 + 1 and +4. Some transition metals form multiple charged ions. The metals in the lower part of the p block also act in this manner, as we see for tin, and lead. In general, metal cations are given the same name as their neutral metal. For example, the cation produced from sodium, simply called sodium ion, magnesium ion. However, transition metals can have more than one charge. For example, iron can be both 2+ and 3+. Historically, iron was called ferrous, 2+ was called ferrous ion, and 3+ was called ferric ions. and sometimes referred to in this manner. Similarly, copper 1+ is cuprous, and 2+ cupric ions, although you'll encounter these names occasionally. The more modern way of designating these is with Roman numerals indicating their charges. Let's do one example here. Name the following 3 cations from the chart. We could see that silver, Ag, forms only one ion, +1. Let's call that silver. Lead, however, because it's a possibility of 2 different charges, we have to put a Roman numeral to indicate it's 2+, and lead, similarly, we put the Roman numeral indicating that it's 4+. Anions are ions that have negative charge. The nonmetals, which are located on the right side of the periodic table, and these are the ones that tend to form anions. And they do that to fulfill their octet. Here's the Lewis dot structure of fluorine, has 7 valence electrons. It's in group 7A. So this octet is not filled. So it gains an electron to fill its octet. Now has this neon electron configuration. So now it is stable with a -1 charge. All these, this is a group that's called the halogens. They do the same thing, gain 1 electron, become a -1 anion. They're very aggressive at gaining electron. Oxygen, sulfur, and selenium in group 6A do a similar process, but they gain 2 electrons, sometimes called chalcogens, this group, chalcogens, you might see that somewhere along the line, mentioned in the book. What about group 5A, such as nitrogen and phosphorus? Well, consistent with the pattern that we've seen, they form 3- anions, gain 3 electrons. And notice how we name these when they become charged particles or ions, anions in particular. We drop the last part and add a different suffix, an IDE suffix. Polyatomics are groups of atoms that have an overall charge. They're very stable. Many of these ions, such as acetate and phosphate, are essential to life and very common in many different materials and applications. The formulas for these are most common are in this table, and you always have this reference table, but you should be familiar with identifying these, that they are not monoatomic ions, but these are polyatomic ions. As you'd see, most of them are anions, negatively charged, with the exception of ammonium, which is the only positive polyatomic that's common. Most of these contain oxygen. and therefore they're called oxyanions. We name oxyanions by adding the suffix "ate" at the end to the root of the element. For example, carbonate and phosphate. Some elements form more than one oxyion. For example, we have in the case of nitrate and nitrite. Chlorine actually forms 4 oxyanions. These names are chlorate and chlorite and perchlorate and hypochlorite. And these prefixes you may see elsewhere, meaning high or max with the per, and low or least with hypo. So you may want to stop the video and just to remind yourself that you can fill in this chart right here with number of protons, looking at the periodic table, number of electrons, how many valence electrons these have, and their oxidation numbers. As you continue in our study of chemistry, it's essential to know the structure, the formula, and charge of common monoions and polyatomic ions. These tables provide a summary of the most important ions. These tables provide, you'll be provided, for the most part, in form of a periodic table and a table of the most important polyatomics. So why do atoms form bonds? Well, the simple answer is to become more stable, to complete their valence shell electrons, and to obtain the noble gas configuration. Depending on the type of element involved, bonding may be ionic, covalent, or metallic. Opposite charges attract each other. Positive and negative ions, when they come near one another, they stick tightly to one another. The force of attraction of opposite charges is, in fact, the force that form ionic compounds, the ionic bond. A compound composed of oppositely charged ions is an ionic compound. And these ionic compounds contain metals, cations, and nonmetal anions. Ionic compounds contain many cations and anions joined together, forming the ionic bonds. To understand how these fit together, let's look at the structure composed of sodium and chloride ions. A single sodium ion and a chloride ion adhere to each other for an ionic bond. But what happens is additional ions present pack together to form an alternating positive-negative charges, eventually forming a three-dimensional array, positive and negative, called an ionic lattice. To represent the composition of compounds like this one, we use a chemical formula that indicates the type and amount of each element present. We represent the ionic compound with a specific chemical formula called the empirical formula. Empirical formula gives the smallest whole number ratio of the atoms in the compound. Subscripts written indicate the number of those ions present. The empirical formula gives the smallest number in a formula unit. We see here sodium chloride and its formula unit. When there's a subscript 1 in a formula, we do not need to show that. It's assumed that there's a 1 here and a 1 here. In fact, sodium chloride is just a 1-to-1 of the cation and anion neutralizing to form the formula unit. And its repeating unit here in the crystal lattice of sodium chloride. Some ionic compounds contain anions and cations that have different charges. For example, considering the solid composed of potassium and sulfide ions. Potassium has a +1 charge, while sulfide has a 2- charge. To form the neutral solid, the positive charges must equal the negative charges. In order for this to happen, 2 potassium ions form with each sulfide ion. So when writing the empirical formula for this ionic compound, we write K2S. We can also predict the formulas for ionic solids containing polyatomics. For example, predicting the formula unit that will form with calcium cation 2+, and nitrate. We write the formula as calcium nitrate, 2 nitrates, and we put parentheses around it so it can be read without confusion. Let's do one more example. Write the formula for the compound composed of aluminum and sulfate ions. Aluminum, we go to the periodic table, we know that it had 3 valence electrons, it loses them to form a aluminum 3+ cation. And sulfate, from the table that we provided, sulfate is a 2-. To make the positive charge cancel with the negative charge, we need to think how these 2 ions will combine to form a neutral formula unit. And the answer is with 2 aluminums and 3 sulfates, forming aluminum sulfate, and here's the formula unit for that. To name ionic compounds, we give the cation followed by the anion. So for sodium chloride, shown there, always think of sodium chloride when we think of table salt. We could say that to remind ourselves that the chlorine has to be changed to chloride. And we state the metal first. Compounds containing polyatomics, in a similar manner, we state the metal first and then the polyatomic. for magnesium sulfate. For transition metals with more than one possible charge, it's important to include the charge in the ion in parentheses in the name when written. So for copper, +1, and we could predict that's a +1 because chlorine, when it goes to chloride, it is always 1-. That means the copper has to be +1. So that's how we write the copper 1 chloride. And for this one, we know it's going to be copper 2 chloride. And we should be able to write out with some information, recognizing that's nitrate, a nitrite. And we could figure out that that means this has to be ferrous or iron 2+. And we could figure out the name. Now, what about to write the empirical formula for ammonium sulfide? Ammonium sulfide. So ammonium is a polyatomic. We could see it on the polyatomic list. It is +1. Sulfide, we should be able to figure out, seeing that it's in group 6A, meaning it's going to be that kind of ion. How do we combine these? Well, it's going to be 2 of these, 2 ammonium ions, cations, forming ammonium sulfide. And you could stop the video and practice a little more with these. So in summary, with what we've just spoken about, ionic compounds and ions. First, ionic bonds occur between ions of opposite charges. Compounds that contain ionic bonds are called ionic compounds. In an ionic compound, the total charge must be equal to 0. And finally, cation is reserved for a cation, anion are the names for positive charged particles and negative charged particles, respectively. It's important to be able to name the compounds by their formula, and given the name, be able to write the formula unit. When non-metal atoms combine, they do this with covalent bonding. Covalent bond, 2 electrons are shared between 2 atoms. Electrons are not lost and gained, but they are shared. For example, consider the bonds between 2 hydrogen atoms. Each hydrogen atom has 1 electron. If we drew the Lewis dot diagram for that, be shown here. To form covalent bond, the 2 electrons pair up. In the space between the 2 nuclei, the force of attraction between the nuclei and from the 2 electrons stabilize this sharing, and we represent this with a dash, and that is a single bond. Remember that first energy level only contains 2 electrons. By forming this covalent bond, the hydrogens both complete their valence level. When 2 hydrogens combine, this is now called a molecule. And now call the molecule in the bonds is stable, and this is one of our diatomics, one of 7 mentioned. We'll mention them again, but there are 7 diatomics that exist. Hydrogen is the lightest and the first one, and we have chlorine, bromine, fluorine, and iodine in group 7. And we also have nitrogen making up most of our air, and oxygen. 7 diatomic elements. So we've seen the non-metals. Non-metals form these covalent bonds by sharing electrons. Let's look at the second example, is fluorine. Fluorine contains 7 valence electrons and therefore needs 1 more electron to complete its valence level. 2 fluorines each share 1 electron and form 1 bond. By forming this bond, they now have their valence shell filled to satisfy the octet rule. And we see that in the Lewis dot structure right there. And that's what these magnificent 7, the diatomic molecules, do. They share electrons to complete their octet. They share it in slightly different manners, but they do share them. And in fact, we can write them like this as well. You could think about why these are, in fact, what they are. Single bonds, double bonds, triple bonds. Based on the valence electrons that they have and the way that they share electrons, this is how they would look. Hydrogen and fluorine are 2 of the elements, the diatomics, and you could see how we've seen how they form their bonds. And sometimes, as I just disclosed there, they share more than just 2 electrons. Sometimes they share 2 pairs of electrons, and sometimes 3 pairs of electrons, as in nitrogen. Discuss that later on in the course. Covalent bonds form when elements combine through covalent bonds. In the water molecule, an oxygen atom covalently bonds with 2 hydrogens. The valence level of the hydrogen is filled by the 2 electrons. What about the oxygen? The oxygen has 4 unshared electrons and 2 covalent bonds. Between the unshared and the shared electron, oxygen has its 8 valence electrons, having 2, 4, 6, and 8. And the hydrogen has the 2 it needs for the first energy level, 2s. Now let's look at this example here. How many electrons does nitrogen atom share in these bonds? Does this nitrogen have its octet complete in Lewis dot structure? Each dash represents 2 electrons. We could see from the structure nitrogen forms 3 covalent bonds to hydrogen because each dash line is 2 electrons. It has 6 shared and 2 unshared. Combining them, it does have its 8 complete octet. We often describe covalent compounds as being molecular compounds or molecular formulas. This type of chemical formula gives the actual number of atoms rather than the simplest whole number. For example, hydrazine, a rocket fuel. This contains 2 nitrogen and 4 oxygen atoms. The empirical formula is of the compound, the simplest ratio would be N2. However, chemists prefer writing this in the molecular form, showing exactly the number of atoms in the actual molecule. Covalent bonds often lead to complex structures. Consider the molecule octane, a component of gasoline. One of the molecules of octane contains 25 different covalent bonds. Larger compounds contain hundreds and thousands of covalent bonds. Because of this complex bonding, elements can combine in many different ratios. Each having unique bonding arrangement produces a unique compound. For example, this table, we have several compounds that form between phosphorus and oxygen. Covalent compounds containing only 2 elements are called binary compounds. These compounds are named in a manner just like the ionic compounds with a couple of differences. For example, let's name these 2 compounds. When naming binary compounds, we first identify the element that's further down or to the left on the periodic table. This element is named first. In this example, we named phosphorus first, and then second is the chloride. Because covalent compounds can form in different ratios, we have to use a prefix before each element. However, if the prefix for an element that's first is 1 for mono, we drop that. And that's the case here. If we were to name these compounds, we're dropping, we don't say monophosphorus, it's just phosphorus trichloride and phosphorus penta for 5 chloride. Now let's look at some more examples. Nitrogen and oxygen form 2 covalent compounds right here. Each of them, their names, nitrogen dioxide, so it's similar to carbon dioxide. And here we have dinitrogen tetraoxide. tetraoxide. Notice we drop the A here. If we have oxide, we don't have a valve and a vowel and a vowel. Drop the first vowel. So let's summarize some of these ideas. Covalent compounds have shared electrons. Covalent compounds are between nonmetals. Most covalent compounds form discrete molecules. And remember, as opposed to networks or lattices in ionic compounds, we can describe molecules using Lewis structures. The Lewis dot structure here shown for water. And we show the shared electron and what's called the lone pair electrons here. Unlike empirical formula, which shows the lowest number of the ratio of the atoms, in molecular formulas, we show the number of each of the atoms in the molecule. Finally, when naming binary covalent compounds, we name the element that is further down and to the left on the periodic table first, and then the second atom with the appropriate prefixes before. Earlier, we explored ionic and now covalent. So let's just put together some key ideas here. In order to fulfill the octet, atoms can either gain or lose electrons or share through covalent bonds. Covalent compounds, atoms, we share electrons. Covalent compounds are between nonmetals. We generally describe covalent compounds with molecular formulas that indicate exact number of each atom contained in the molecule. In ionic compounds, they form between oppositely charged ions. They don't form discrete molecules. And we describe ionic compounds in its formula unit or empirical formula. That's the simplest whole number ratio of the cations to the anions in the compound. The differences in ionic and covalent compounds lead to many unique features, physical properties in substances. For example, limestone, it's composed of calcium carbonate, ionic compound. Olive oil is composed of covalent compounds, covalent molecules containing carbon, oxygen, and hydrogen. Properties of any compound, from hard, solid to like limestone to liquid, like olive oil, arise from the elements and the connectivity of those atoms. Because of this, it's important to be able to distinguish between ionic and covalent compounds clearly. Covalent being all nonmetals, ionic, a metal and a nonmetal. It also contain polyatomic ions. And distinguishing among these that are shown here, magnesium fluoride, ionic. And we can name them like so. Diphosphorus tetroxide, covalent, both being nonmetals. Ionic, iron 3, ferric nitrate. Sulfur hexachloride covalent. One of the most important differences between ionic and covalent compounds is how they behave when they're combined with water. To understand the important difference, let's begin with some fundamental ideas. When a substance such as a sugar or salt mixes with water, it disperses through the liquid, forming a homogeneous mixture we call a solution. If the liquid is water, we call it an aqueous solution. What happens when a solid is dissolved? Compounds that dissolve in water are said to be soluble in water or water soluble. And those that do not dissolve in water are said to be insoluble. An aqueous solution is also a homogeneous mixture. Pure water is a pure conductor of electricity, for example. But connect a battery and a light bulb with pure water, as shown here, the light bulb will only dimly light. However, if we dissolve an ionic compound like sodium chloride in the water, results the solution conducts electricity much more efficiently. It's evidenced by a bright light. Because of this property, we refer to aqueous ionic solutions as electrolyte solutions. And ionic compounds act as electrolytes. When ionic compounds dissolve in water, the positive and negative ions pull away from each other and they're surrounded with water. And they are said to be disassociated. As a general rule, covalent compounds do not form ions in water. Because of this, aqueous solutions containing only covalent compounds are not electrolytic. Although most covalent compounds do not form ions when they dissolve in water, there are some very important exceptions to this rule. Acids are covalent compounds that produce hydrogen plus ions in aqueous solutions. If we dissolve HCl in water, the HCl dissociates to hydrogen ion and chloride ion, hydrochloric acid. If we dissolve nitric acid, HNO3 in water, forms ions of nitrate and hydrogen ion. Here are the formulae and names of common acids. And they each, in water, in aqueous solution, dissolve or dissociate into hydrogen ion and their counter anions. Binary acids consist of hydrogen ion and a single non-metal element, such as those shown here, sometimes also called mineral acids. And named thusly with IC suffix and acid and a prefix of hydro. Oxyacids are compounds that dissociate to form hydrogen ions and an oxyanion. And there are rules for these. Rule 1 is the anion ends in 8, and the suffix to the acid is ic. For example, the NO3 is called a nitrate. The corresponding acid, nitric acid. Similarly, carbonate, the acid is called carbonic acid. Other acids named similarly: sulfuric acid, phosphoric acid. Naming oxyacid rule 2, when it ends in ite, the acid, we change the suffix to OUS or us, as in nitrous acid and chlorous acid. Let's quickly summarize these ideas. Electrolytes and compounds that form ions when they dissolve in water. When ionic compounds dissolve in water, the ions dissociate and are split apart. Most covalent compounds do not form ions in water. They are not electrolytes. However, it's important, one exception are the acids that form H plus ions and the counter anion.